na naka-compression. Okay? Pero yung alam natin na pinaka-basic na compression member is the column. That is why, dito, parang masyado siya nag-concentrate on columns. Which is ganun din naman sa other. Ano. Pero di ba, if you remember your structural theory, ganyan. Diba, chine-check natin the member forces. Ganyan. Okay, sa mga trusses. Ganyan. Some of which are in tension. Okay, some members. Usually, ito, mga to. Yan, ay naka-tension. Okay? Tapos, usually yung mga top chords, itong mga top chords na to, these are in compression. So, when we design the tension members of a truss, then gagamitin natin yung pinag-aralan natin nung last chapter, no? Or last module, yung design for tension. Okay, when we design the compression members of our trusses, ginagamit naman natin itong module na ito. Okay, or yung mga specifications na naka-state dito sa design for compression. Okay, and columns, of course. No? And there are also other compression members din, guys, na mamimit nyo. Okay, later. So, this chapter covers the design philosophies to be used in the design for compression of steel structures. Okay, so in the end, you have to be able to design a steel column for a given loading, describe the local or local buckling, or no, tama, and calculate the local buckling capacity of a column. Bakit local? And then determine the design strength of columns in braced and unbraced lengths. No? So, itong design strength. Pero i-consider natin ang ano din class, ASD. Bakit design strength lang nilagay ko dito? Okay, so here's our learning focus. So, of course, compression members are structural elements that are subject to axial compressive forces only. Axial compressive plus, alam niyo naman yung difference between a tensile and an axial. Diba? If this is your member, tensile is that force which will tend to elongate our member. Okay? For compression, okay, that would be the stress, okay, or force that will tend to contract, no? Or compress yung ating structural member. Okay, so this is compression. So the stress in the column cross section can be calculated. So it is always the same, no, in our mechanics of deformable bodies. Okay, that for axial and tensile stress, parehas lang ang formula. That is, stress is equal to P all over A. Diyan lang naman yan galing lahat, class. No? Lahat ng pinag-aaralan natin sa structural design, it is always derived from the basics of mechanics of deformable bodies at yung Newton's laws. Okay, so where F here is it is assumed to be uniform all over the entire cross-section. So it is an assumption, no, that the stress, okay, or the compressive stress induced by loads is uniform, okay, all throughout the cross-section. Ibig sabihin, if this is our circular column, no, yung stress or yung stress ay equally distributed dito sa buong cross-section. Ganyan. Pare-parehas yung intensity ng pressure. Okay? The ideal state is never reached actually. So the stress state will be non-uniform due to, sabi niya, hindi naman daw talaga yan na-achieve. Okay? Na uniform yung stress distribution doon sa ating structure talaga. Why? It is because of accidental eccentricity of loading, no? Eh, ganun din naman talaga, hindi mo naman may eksakto na doon talaga sa centroid mag-a-act yung load mo. So, eccentricity, okay, will is not or is inevitable. And then our members are out of straightness, no? Or crookedness. Yung constructability ng ating materials, hindi naman natin masasabing perfect. So, there could be out of straightness. And we have residual stresses in the member cross-section due to fabrication processes. So, yun. So, accidental eccentricity and member out of straightness can cause bending moments in the member. However, those are secondary. Sabi niya dito ha. Those are secondary and so does usually ignored kasi maliit lang yung effect nila plus sa design na pwede mo na siyang i-consider as negligible. Now, bending moments cannot be neglected if they are acting on the member. Members with axial compression and bending moment are called beam columns, and we have different specifications or different module for such beam columns. So the strength of a column depends on the following parameters. Nahihirapan si Christian Joy pumasok. Laging pumapasok tapos nagle-left. So the bending moments cannot be neglected if they are acting on the member. So members with axial compression and bending moments are called mali. The strength of column depends on such parameters. The material of the column. Siyempre, kung ano yung ginamit nating material, is it tawag nito, concrete or steel, since we are in steel, no? So, steel yung gagamitin. And, of course, when we say steel, iba-iba din ang properties, no? Depending on the kung high strength man yan or what. And then the cross-sectional configurations, of course, are we going to use wide flange beams or S-shape or what for our column? Are we going to use built-up members? No? And of course, the length of the column also will or nakaka-epekto ng malaki doon sa strength ng ating member. And the support conditions, are we going to fix it all throughout its member span or pwedeng half fixed and then half pinned or free to translate and then fix, mga ganyan, no? We have factors to consider for those support conditions or what we call the restraint conditions. And then, of course, residual stresses and imperfection because the material, okay, is not isotropic and homogeneous. So, geometric variations for columns, no, we have geometric variations for the columns and eccentricities of loading. Those are imperfections, okay, and they affect the strength of our column. Now we have buckling. So if we consider a long, slender compression member, ito yun, no? If this is a long and very slender, so na yan. And if an axial load P is applied and increased slowly, it will ultimately reach a value PCR that will cause buckling of the column. Okay? So imagine yung, di ba, ano ba usually yung ginagamit nating example for this? Yung ruler class, di ba? Kapag nag-apply ka ng, di ba, hinawakan mo lang dito and then dito. then you apply a compressive force, it will tend to buckle like this. Diba? Ito yung buckling na sinasabi. It is like a, parang ano siya, parang beam siya kung papahiga mo. Okay, but it is not subject to bending load, no? Or yung ganyan na loading. Hindi ganyan. Okay? You applied a load here, and then magde-deflect siya like this. This is what we call buckling. Okay, so buckling occurs when a straight column subjected to axial compression suddenly undergoes bending. So bending, ibig sabihin, nag-bend na siya. Something like this. So it is not bending like in our design for bending, but it is due to the axial force. That is what we call buckling. So buckling is identified as a failure limit state for columns. So it is a failure limit state. Remember, we have three failure limit states doon sa ating tension members. Those are the yielding of the cross section, the rupture of the net section, and block shear or block shear rupture. Diba? Tatlo yon. Here we have uh, dalawa. Okay? And those are both buckling state. So buckling of actually loaded compression members. Ito yan. So the critical buckling load for columns is theoretically given by equation 4.1. This class, ito, ay nakikita din natin doon sa ating, or it should be part of the discussions in the mechanics of deformable bodies subject. Kaya lang, hindi na natin na-cover ang columns doon kasi. Okay, so it is class derived or si ano ang nakadiscover dito? Si, if there is pi, it is always Euler, no? Or Euler, sabi ng iba. It is Euler. Ang tamang bigkas daw. Sabi ng mga experts. Okay, so pi of course is the pi number, that's 3.14 something something, no? And then E is the materials modulus of elasticity, alam niyo naman yan. I is the moment of inertia about the axis of kung saan siya magbabakel, no? We will consider those. Okay, that's moment of inertia. K is the effective length factor. Okay, and yung K na yon ay nandito lang naman. Dito natin yung mahanap. And L, of course, is the length of the column, no? That that quantity squared. Okay, so the effective length factors are given on this table daw in the AISC manual. Okay, AISC class is the American Institute of Structure. Tama ba? Daming kandidato. Ano na nga ulit ang AISC manual? American Institute of Steel Construction. Okay. So for members designed on the basis of compression, the effective slenderness ratio, KL over R, preferably should not exceed 200. Okay, so we have a slenderness ratio class that na kino-consider natin. Okay, so in design, okay, di ba meron din tayo sa tension, and it should not exceed 300. Dito naman, it should not exceed 200. Okay? Para masabi nating slender yung ating, or non-slender yata. Tama. Yung ating member. So this is our K factor, theoretical K value. Usually, class, yung ginagamit natin for now is the theoretical K value. Okay? When we design, dito na natin gagamitin ito. Okay? So, if it is, nandito yung mga legends, no? Kapag ganito, it is rotation fixed and translation fixed. Alam niyo naman yan, that is fixed. No? There is no translation and there is no rotation. Okay? Ganito, there is translation, that's pin class. That's rotation free. Diba? Ang pin pwedeng mag-rotate but cannot translate. Okay? Translation fixed. Yan. Now here, this is rotation fixed. Hindi siya pwedeng mag-rotate but it can translate. That's translation free. Okay? Yung ganito. Okay, and then this part is rotation and translation free. Ibig sabihin, that's free. Walang restrictions, walang support yan. Okay, that is this case. Okay, for such cases, we have different values for K. Okay, dito, the K value is 0.5 for both ends fixed. No? Both, tama, fixed sa both ends. Okay, so 0.5 ang value ng K. If it is fixed and pinned, it is 0.7 class. Okay? If it is fixed and translation free, ito translation free, usually naman sinasabi naman yan sa mga problems. If it is fixed all throughout its member or length or its ends, or is it pinned or is it pin and fix or free and fixed, mga ganyan. So ito, 1.0 for this case. Okay, for the pinned on both ends, yan, 1.0 din. Okay, if it is fixed and then free, 2.0. And so for pin and then rotation fixed but translation free. Okay, 2.0 yung mga K values. Mga yan. Jason Lee makalangdang. Then now, if we apply the critical load, ito yung PCR. Ito, daw. No? The elastic buckling stress is obtained. Kapag daw class, ang in-apply nating load ay that load kung saan magbabakel na yung ating member like this. Okay? Ang stress na mag-occur sa ating member ay what we call the elastic critical buckling stress. Ito. Okay? Is obtained. And anong formula niyan? Ito na yan. Pi squared E all over KL all over R squared. Okay? Yan ang ating elastic critical buckling stress. Ayan ang lagi natin ginagamit now. Iba na kasi class, because what we use now is NSAP 2015. Okay? Yung last batch, if you still know them, yung batch ni Natami. Okay? Nung nagturo ako ng steel design sa kanila, ang ginamit kong code is NSCP 2001, which is obsolete, no? And pinagsisisihan ko siya kasi nung nag-exam na yung mga classmates ni Tami, ang ginamit na code is NSCP 2015. Okay, ang prediction ko kasi is they will still use NSCP 2001. No, kasi nung nag-exam ako nung 2016, ang gamit pa rin, wherein meron ng naglabas na sila ng NSCP 2015, hindi pa rin ginamit yung 2015. They still stick to 2001, while meron naman ng noon, NSCP 2010. So now, kailangan natin pag-aralan lahat sa NSCP 2015. Now, inelastic column buckling. So equation 1, ito class. This is your equation 1. Your critical buckling load, PCR, is valid only when the material everywhere in the cross-section is in the elastic region. Alam niyo naman, class, kung ano ang elastic region. Huh? When a material fails, okay, this is elastic, okay, it is linear, and then it will fail like this, right? So the elastic region is along this region lang. Okay? So if the material goes inelastic, then the equation 1 becomes useless and cannot be used because, yun nga, hanggang doon lang siya sa elastic region, yung equation 1. Now, what will happen in the elastic region or the inelastic range? So we have several other problems that appear in the inelastic range. What are those? The member out of straightness has significant influence on the buckling strength in the inelastic region. So it must be accounted for. What else? The residual stresses in the member due to fabrication processes or errors will cause yielding in the cross-section much before the uniform stress. Mag-yield daw muna siya bago pa maabot yung yield stress Fy. Okay? And then the shape of the cross-section will also influence the buckling strength, whether we use W sections, C sections, or any other section. So in the inelastic range, the material, okay, our steel material, will undergo strain hardening. Okay, dito. Ito, this is elastic range. Okay, and then the other part is now inelastic. And in this case, magkakaroon na siya ng strain hardening. Now, what are the requirements by the National Structural Code of the Philippines? The nominal compressive strength shall be determined based on the limit state for flexural buckling. Okay? At anong sinasabi doon? The nominal load will be that equal to our critical elastic buckling stress, FCR, multiplied by, or no, that is not elastic, that's critical, multiplied by the gross area. Okay? The design strength for columns for the flexural buckling limit state is equal to P sub C. This is our reduction factor for compression multiplied by P sub N. This is for LRFD class. When we say design strength, that's LRFD. Okay, this is for LRFD, design strength. And for allowable compressive strength, of course, when we say allowable, that is now ASD. So this is the ASD counterpart. That's P sub N, that's the nominal compressive strength divided by the omega C or the factor of safety for compression. Okay? At ano bang sinasabi? P sub C for LRFT is 0.9 for compression and 1.67 for ASD. Sir, hindi ba katulad ng tension member that we use 0.9 or ano ba yung isa? 0.75 for rupture and 1.67 and 2.0. Hindi yun class. Okay? For compression or for design for compression, iisa lang yung gamit natin. It is either 0.9 or 1.67. Okay? So the flexural buckling stress, FCR, is determined as follows. Okay, this is how we compute for FCR. KL over R, that is our slenderness ratio. Okay? Paano yun hanapin? K is the factor. Yun yung K dito sa ito. Okay, that is the effective length factor. L, of course, is the span length. Okay? And then R is the least. Okay? Yung mas maliit na ating or hindi naman. Okay? Because we will consider the major and minor axis. So, okay lang. We will use R sub X and R sub Y and consider everything. Okay? So, KL over R is our slenderness ratio. Okay? And if it is less than or equal to this value, 4.71 square root of E all over Fy, okay? Or you may consider this computation to determine, no? If this slenderness ratio is less than or equal to this ratio, then we consider our column to be short. Okay? It is short column so that the computation for the critical backplane stress, okay, is 0.658 raised to Fy all over Fe, that quantity multiplied by Fy. Sir, saan galing yan? Binigay yan ng NSCP, no? Na inadapt din sa other international codes, no? Now, if you ask me kung paano na-derive yan, hindi ko alam, class. Okay, pero yan yung gagamitin natin. Alright? Doon sa NSCP 2001, hindi na yan ginagamit. Or, hindi ganyan yung ginagamit doon, no? But we will not talk of the 2001 specification kasi that is very obsolete na. Alright? Now, if the slenderness ratio is greater than that value, 4.71 square root of E all over Fy, we will use a different formula because our column now is considered to be long. It is not short. So that our critical backplane stress, okay, or compressive stress is now equal to, mas madali, 0.877 Fe. Okay, again, the computation for Fe, okay, or elastic critical backplane stress is pi squared E all over KL over R squared. Okay? Do not use this formula. Use this formula. Okay, yung isa. Alright? 16 lang pumasok. Okay lang. Okay, so here guys is, ayan. Okay, L, ito pala yun. Unbraced length yung L. Okay, so this is the region. Okay, so if your KL over R is less than or equal to 4.71 square root of L over Fy, you're going to use this for the critical backplane stress. Now, if it is greater than itong KL over R, ay greater than this 4.71 square root of L over Fy, ito na yung gagamitin natin. Ibig sabihin, mas mababa na yung mako-compute natin na critical backplane stress. Why? Because our column is very long. So that mas maliit na yung kaya niyang i-contain para hindi siya mag-buckle. No? Class. So, by what ratio? When the ratio is about 0.39 for FCR all over Fy. Okay? So, that's about 39% na lang ng ating Fy. Daming kandidato. Alright. Anong klase nyo mamaya kay Engineer Kadang? Lubat. Okay. So here guys, we have major axis buckling or minor axis buckling. Okay. So whichever, we always consider both, no? Especially for wide flange section. We always consider major axis buckling and minor axis buckling. Of course, kung ano yung mas maliit yung kayang i-hold, okay, will govern the design at yun lang yung gagamitin. What is major axis? Of course, guys, ang major axis natin will be this axis, no? For the column. Okay? So, ang bending will be something like this. For white flash, this is major axis buckling. Okay? Kapag naman minor axis, pag ganyan. Okay? I hope you can imagine. Because the minor axis for such is tama. This is a major axis natin for this is the x-axis eh. Pag ganyan. And then ang weak axis natin or minor axis for this is the y-axis. Okay? So, magbe-bend yung y-axis natin na ganun. Ganyan. Ito naman yung axis, x-axis natin. Bend siya. Something like that. Okay? So, you can always imagine it as a beam, but it is subject to axial loads. So, such deflection, okay, or what we call buckling, will, okay, limit our design. Okay, so ito, nandyan din naman sa inyong, ano, ano ba yung mga materials nito na ginagamit natin for uh, compression members. Okay? If we use W section, it is literally A992. Okay? So, binigay ko naman sa uh, ibang modules kung ano yung mga FYQ for A992. Still, it is 850 or 65 yung regulation sa mga lang yan. Mga special. Okay, S or C or MC or L or section. Ah, ito, mga shaded ay mga ano lang, merong mga ganito but they are parang especially manufactured for design purposes, no? Depende sa ano. But they are not commercially available. All right. Nagbasa lang ako. Okay. So we have an example here. Okay, but first we'll have a CR break. 3 minutes or 4 minutes. I'll be back 9 a.m. Okay, class. CR break lang tayo. Okay.
Win gaya.
Hello, hello. Rinig pa ba? Hello? Ayan. Okay, so we have your example one. Okay, we have a W14 by 74, okay, of A992 steel. Yun nga, di ba, class? If it is white flange, it is always A992. And it has a length of 6 meters and pinned ends. So, pinned ends daw, class. Yun yung hint mo for the K factor. Okay, L is 6 meters. Okay, and the section is W14 by 74. For the yield stress, ito yung hint mo dyan, the A992 sabi niya. So, what are the required? We are to compute the design compressive strength. When we say design compressive strength, we are talking about LRFD. So, for LRFD, and the allowable compressive strength for ASD. So, yan yung dalawang unknowns natin. So, for the solution, step by step, I hope okay naman yung ganitong ano. Kasi kinopya ko lang ito sa foreign ano. Pero ka-English kasi yung mga examples nila kaya binago ko. So, inadapt ko yung paano sila mag step by step ng problem. So, we visualize, we have a ano, 6-meter long column. Say this is the 6-meter length. And it is pinned at both ends. Yan, ganyan. The length is 6 meters. Okay. Yan. So, it is pin or pin-pin end connection. Ito no. If we go here, saan yung pin-pin dyan? Ito yung class. Nakapin dito and nakapin dito. So that the K factor is 1.0. Right? So yan. And for the W14 by 74, or any wide flange section, X is the major axis. So for wide flange section class, no? X is our major axis and Y is the minor axis. Okay? So the major axis means the axis about which it has greater moment of inertia. Yun yung basehan natin if it is our major axis or minor axis, yung moment of inertia niya. And for wide flange, it is always the x-axis. So, mas malaki lagi yung I sub x natin kaysa I sub y. Wait lang, I have message. Sir, magkakuna ko, may exam kami ng reinforce ngayon. Deadline ng 11 a.m. So, okay lang, Bird. You can go out para mag-exam. Okay, so Ix is always greater than I sub y. So for W14 by 74, of course, for all steel, E or modulus of elasticity is always 200 gigapascal. Okay? And since our steel is A992, Fy is 345 megapascal. So Fy lang naman class yung ginagamit natin for design for compression, no? We do not use Fu just like design for tension. So for W12 by 50, eto na, no? Mali. Tanggalin mo yan. For W14 by 74 from AISC shapes database, paano maghanap ulit sir ng ano, you go to AISC shapes database, and then you go to W14 by 74. Okay, W14. Ito yung W14 section natin. Hanggang dito. And of course, 14/74 yung hanapin natin dito. Right, I will color it. Yan, that's W14/74. Okay, ano ba yung mga properties na kailangan natin? By area. Ano yung area natin? This is in naka-mm pala to. Naka-inches yung mga unang columns. So we go to the dito, yung naka-mm. The W is weight class. The area is 14,100 square millimeter. So, ito yun. Okay? So, since in our section database, nakalagay naman na doon class, kung ano yung R sub x and R sub y natin. So, we do not have to get I sub x and I sub y. Meron na dyan R sub x and R sub y. Okay, saan ba yun mahanap, sir? Punta mo lang sa kanan. Ito yung R sub x niya, 153. Okay? Siyempre, if you compute that, merong point yan. Pero, hindi niya kayo consider dito. Okay, okay lang din naman. And then, R sub y is 63.0. 153 and 63 yung R sub x at R sub y. So now, we compute the effective length and the slenderness ratio for the problem. So according to the problem statement, the unsupported length for buckling about the major and minor axis L sub x, we will have L sub x and L sub y class equal to 6 meters. Bakit, sir? Sometimes, class, because along the y axis is our minor axis or tama, along the y axis, yun yung weak axis natin. Sometimes, ilalagyan nila ng stiffener. Okay, dito sa somewhere along the length, along the minor axis. Sa major axis, hindi na nilalagyan ng stiffener. Okay. So, for example, dito, may stiffener dyan. So that the effective length now for such case ay mahati. Kumbaga, kung may stiffener along the weak axis, I sub y, doon sa gitna, then this is 3 meters na lang, 3 meters na lang. Okay. Di magbabago yung L sub x at L sub y natin. Yung L sub x natin, since x is our strong axis, 6 meters pa rin yun. Okay. Pero yung L sub y natin, our length along the weak axis, since nilagyan natin ng stiffener, it will now be 3 meters. Okay, ito na yan. So, since parehas lang yan, there is no statement such that there is a stiffening along the weak axis. Then our L sub x, our length along the x or along the strong and weak axis or the major and minor axis is 6 meters. Okay. Then the effective length factor, since our K plus is 1.0 here, our K is 1.0. Our KXLX, that's the effective length along the major axis. That's 1.0 times 6, which is 6 meters. Or, if we express it in millimeters, it is 6,000 mm. So, it's true for the minor axis since wala naman magbabago. Okay. KYLY is also 6,000 mm. Now, what is our major axis slenderness ratio? That's KL over R. Since we are considering the major axis KXLX over R sub x from above. Okay. And that is equal to 6,000 over 153 or 39.22. What about the minor axis? It is KYLY over R sub y. Okay, so After that, you find or calculate the elastic buckling stress. So the governing slenderness ratio, so sabi niya, tandaan niyo, the governing slenderness ratio is the larger of the slenderness ratio along the major and minor axis. So ano bang yung mas malaki? Okay, if you look, we have 39.22 for the major axis and 95.24 along the minor axis. So minor axis yung nag-govern ng slenderness ratio. But plus, remember, when there is a stiffening along the minor axis, sometimes the major axis na ang mag-govern na slenderness ratio. So we still have to compute for such. Hindi yung, sir, lagi naman si KYLY over RY ang nag-govern, so siya na lang yung compute ko. No, you have to compute both minor and major axis. So here, in this problem, it is 95.24. So doon natin, class, i-check for or i-compare on this limit 4.71 square root of L over Fy. But first, okay, the computation for Fe is lang. It is always Fe is equal to I squared E all over KL all over R squared. Ano yung KL over R, sir, na gagamitin? It is the governing slenderness ratio. And sabi nga natin, it is 95.24. So putting the values, no, direct substitution lang, we will have our elastic critical buckling stress to be 217.6 megapascal. Diba? Kita nyo, it is along the elastic region lang. Ano ba yung sagad ng Fy? Okay, for the elastic region, 345 megapascal. Ibig sabihin, class, in our strain diagram, if ganyan yan, ganyan siya, okay, hanggang dito yung Fy is equal to 345. Diba sabi natin that buckling, okay, or design for compression is along the, ano lang, dito lang, elastic region. Pero meron yata yung, mamaya, tingnan natin. Okay, now, we check the limits. Okay, that's 4.71 square root of L over Fy. So, direct substitution lang, meron tayong Fe to be 200 gigapascal. It is always constant for steel. And Fy for A992 is 345. So, input lang yan sa calculator. Then we have 113.4. Now, we compare it. KL over R versus 4.71 square root of L over Fy. And 95.24 versus 113.4, it is less than, no, yung slenderness ratio natin. So that we can say that KL all over R is less than or equal to, or less than, actually, 4.71 square root of E all over Fy. So, hanap natin. Diba sabi natin, if it is less than, the computation for the critical buckling stress is, eto, 0.658 raised to Fy all over Fe of our Fy. So, yun yung factor natin na minumultiply natin ng Fy to get it. So, since alam na natin na yun ang formula, you apply it. So, ito na yung ating formula. So, putting the value of Fy and Fe, yun lang naman yung ilalagay class. To get your critical buckling stress, we now have 177.67, no? So, that's 177.67 of 345. Alright. Now, to get your nominal strength, that's Pn, that is now equal to your gross area multiplied by your critical buckling stress. Since our gross area is 14,100, just multiply it by 177.67, yun yung FCR natin. Okay, you divide it by 1,000 to express it in kilonewton, so that you have 2,505.15 for the nominal compressive load or compressive force that our column can handle para daw hindi siya mag-buckle. Okay. Wait lang, class. Okay. All right, now we check for the design strength and the allowable compressive strength for LFD and ASD. So the design strength, yung P sub n, i-multiply mo lang ng ano, ng reduction factor, that's 0.9. So 0.9 of 2505, then we have 2254.6. Yun na yung ating design strength class. For the allowable strength, i-divide mo lang siya ng 1.67. Then we have 1,500 kilonewton. Ni-round off ko na lang yan, class. It might not be exactly 1,500. Okay? So, ganyan lang on how to find the design strength. Okay. So, the mode of failure considered so far is referred to as flexural buckling because, di ba, nagbabuckle yung ating member actually due to compressive force. So, as the member is subjected to flexure or bending when it becomes unstable. So, for some cross-sectional configurations, the member will fail by twisting, torsional buckling, or by a combination of twisting and bending, or what we call flexural torsional buckling. Now we go to the local buckling limit states. The AAS
Sir,
uses the
excuse me,
column
sir.
strength. Yes.
Sir, screen.
Oh, what the? Okay, now we consider the local buckling limit state. Okay, sabi ng AISC, the column strength assumes that column buckling is the limit state. Column buckling. However, sabi daw, the column section is made of thin or slender plate elements. Diba? Our wide flange, our widely used column member ay okay. Currently, ano na lang yung yellow figure. Then may erase that. Okay, so we have the wide flange section here. Yung naka-eye. Okay, anong sabi ni okay, may class binigay ko na nga lang yung link sa TC eh. Mag-work pa ba si Mutin sa Seymour? So, sabi dito, however, the column section is made of thin slender plate elements, then the failure can occur due to local buckling of the flanges or the web. Ano ba sabi ng local buckling? Okay, yung flange, pwedeng part of it ay mag-buckle or mag-fail. Diba? Merong distortion na nangyayari. Example, ito, bumigay. Ito na ganyan lang siya. Partly lang. No? Makikita natin dito. May figure yata dito. Ito, plus. Kung makikita nyo, yung flange, no? Part ng ating member. Okay. This is a column ha. Pinahiga lang siya. Okay. Part of it ay nag-fail na. Okay. Without even reaching class, yung bending yung backling na ano na magbe-bend yung whole member. Okay. In this case, ayun, namatay na yung aking laptop. Balik ko lang. Okay. Pwede din class na doon sa web magkaroon ng failure dito. Diba? Magkakaroon na siya ng distortion dito sa part na to. Ganyan. Pwede ganun din yung failure niya. And this is what we call local backling. If local backling of the individual plate elements occurs, sabi niya, then the column may not be able to develop its backling strength. Okay, therefore, the local backling limit state must be prevented from controlling the column strength. Sabi dito, dapat daw pigilan natin na mangyari ang local backling. So the local backling depends on the slenderness or the width thickness B all over T ratio. Ayaw na mag-open ng ano ko. Rinig niyo pa ba ako, class?
Yes, sir.
Okay. Okay. What is this width to thickness B all over T ratio? Makikita natin to sa NSCP. Okay. Saan yun, sir? On specification 502.4.1, okay, considering tables 502.4.1 and 502.4.2, okay, of our NSCP, that is in chapter 5, okay? Saan ba yun? Dito. Okay, and if I go to page, bakit find yun? Ayan. Wala na. Restore. Yeah. Alright, I'm back. Paano pumunta ng page dito? $600. Okay. Hindi pa yun. 502.4.1. Okay. Let me go to 502.4.1. Okay. Ito yung sinasabi ng 502.4.1. Classification for all sections for local backling. So sections are classified as compact, non-compact, or slender element sections. So for a section to qualify as compact, its flanges must be continuously connected to the web or webs, and the width to thickness ratios of its compression elements must not exceed the limiting width to thickness ratio lambda p. Right. Paano ba sukatan ito? Okay, basahin na lang natin. Hindi ko siya masulatan. From tables 502.4.1 and 502.4.2. If the width to thickness ratio of one or more compression elements exceeds lambda p, but does not exceed lambda r, the section is non-compact. Now, if the width to thickness ratio of any element exceeds lambda r, the section or six, the section is referred to as a slender element section. So now we have three classification for section: compact, non-compact, or slender elements. Now, if we go to the table 502.4.1, eto. This is for stiffened and unstiffened element. Table 502.4.1 class is for unstiffened elements. And for stiffened elements, we have 502.4.2. Ano ba yung diferensya ng stiffened and unstiffened, sir? Ang stiffened, ibig sabihin, on both sides, no, ay supported siya. Meron naman pala sa module, nakalagay doon kung paano ang stiffened and unstiffened elements. Check natin. So, ano sinasabi? Each plate element must be stocky or stocky enough, or it should have a BL over T ratio. Ano yung BL over T ratio, sir? Ito yan, class. Hindi natin i-consider yung mga flexure, no? If you read or dito 502.1, number 1 is flexure. Okay? So, we do not consider that. Number 2, that's the flexure. Saan natin gagamitin, sir? Sa bending pa lang yan. Gagamitin. Sa next module. Okay? Doon tayo sa extensive compression. Number 3, uniform compression in flanges or section. Ito, compression natin. Compression. Number 4 is compression. Number 5 is compression. Okay. Number 6 is flexion. So, hindi natin i-consider yun. Right? Ayan. And then, for stiffened elements, number 7, hindi natin yan. Tama. Yan. Number 9, flexure yan. So, hindi yan kasama. Number 10 is compression. So, kasama. Number 11 is flexure. Number 12 is compression. Okay, so kung consider natin for stiffened elements ay number 12 lang for HSS. Okay. Number 10 for uniform compression in webs of doubly symmetric I-shaped sections. Okay. Webs. So, webs naman yan. And number 8 for piece. Alright. Ayun, BL over T. Ito yung mga BL over T. Sometimes it is, for example here, for case 8, hindi ko kasi siya ma-highlights eh. Yun pala, screen right. Okay. Yung mga B all over T na sinasabi natin, in this case, yan yung depth all over thickness of the web for compression. At ito din, spatial over TW. Okay? Yung mga yan. Discard. Okay? At ito, B all over T din. Okay? At makikita mo naman dito class sa left or sa right kung ano yung mga B at T na yan. Okay? Ano yung mga H tsaka thickness of the web na yan. Okay, of course, thickness of the web, makikita mo yan sa database. Yung H, so consider natin ito. Eto, yung slenderness, hindi slenderness. Itong ratio na ito, H all over T sub W, no? Paano natin hanapin yung H? Yung T sub W, yan yung thickness ng web ng section na ito. Okay, yung H. Okay. Second part na ito, class. This is K. Makikita din natin sa ating NSCP. This is also K. Okay. So, for that, the H that is equal to the overall depth. This is equal to overall depth. That is equal to the overall depth. Makikita yan sa extension database. Minus 5. This is K. Ano ba yung tracer? Yan yung center ko yun. Okay. Yan yung center class. Kapag tututo yung reflection mo in PT. Okay. Ulit yan sa neutral axis. Sensor lang ng kalahating T. Okay. Yan yung distance K mo. Doon sa section database. Tingnan natin section database. Ano yung finisher? Makakaroon lang yun. Okay, nandito siya. So, niloloko ko lang kayo. I think yun yung Y for the T. Okay. Parang dun sa tension natin. If you go to the T, W14 by 74, yung kalahati niyan would be W or T, WT 7 by 74 divided by 2. 7 by 37. You go to WT. WT 7 by 37. Alright, ito. Yan. We look for Y. Ito yun, 33.5. So, 33.5 yung distance K na ano yun? Ito. Itong distance from the flange up to the itong H na ito. So, yun yung depth minus 2K yung ating H. Okay? So, partly, na-discuss naman na natin yan sa ating design for tension. Alright? What's next? So, those are the V all over T ratios. Now, the NSB specification, nabasa natin yung kanina, provides that the B all over T and H all over T limit that the individual plate elements must satisfy so that local buckling does not control. For compression, the NSCP specification provides the slenderness limit lambda R. Ito yung sinasabi nga, yung lambda R daw, okay, for the local buckling of plate elements. Okay? So for local buckling, ang basehan natin is the B all over T or H all over T ratio class. Okay? And kino-compare natin siya for the lambda R. Ano ba yung lambda R? For compression, diba ano ba yung mga compression natin dito? Number 3, yung lambda R natin, let me, yeah, doodle. Alright, ito. So for number 3, so number 3 lang naman yung and the other dun sa baba, yung compression dito. The ratio is B all over T. Ano ba yung B? Kalahati ng flange thickness or flange width class. Okay, that's BF all over 2. Okay, ano yung T? Thickness of the flange. So that, yung B all over T na sinasabi dito, that's why in section databases, pwedeng makikita nyo, ganito siya, BF all over twice the thickness of the flange. Yan yung ratio na yan, class. Okay, that's the B all over T ratio na sinasabi dito. Okay, at saan natin siya kino-compare? Sa 0.56 square root of E all over I all over Fy, yung lambda R daw. Yun daw yun. Okay, doon lang natin kino-compare for the para makita natin kung mag-govern ba ang local buckling or not. Alright. So if the slenderness ratio B all over T of the plate element is greater than lambda R, then it is slender. And it will locally buckle in the elastic range. No? So ayaw natin ng ganon. Our ratio, B all over T, kung yung B all over T daw natin, mas greater sa lambda R, it is slender. And it will locally buckle. Okay? So, iba na yung consideration for the design yan. Yung mga formulas natin sa taas na i-consider nila, hindi na effective. Now, if the slenderness ratio B all over T ay less than lambda R, but greater than lambda P, then it is non-compact. Anong ibig sabihin nun? It will locally buckle immediately after reaching Fy. So, okay lang. No? Pare-reach nyo yung Fy daw, and then at this point, magbabuckle na siya locally. Di okay lang. Why? Because buckling or the ano ba tawag natin kanina? Nakalimutan ko yung flexural buckling. Ito pala. Bending buckling kasi yung ano ko naiisip ko. Flexural buckling naman class ay mag-o-occur before pa ma-reach yung Fy. Diba? Saan ba yung graph natin kanina? Dito. Okay? Ito yung ratio ng FCR all over Fy. Ang tawag nito yung critical buckling stress that which magkakaroon na siya ng flexural buckling ay along the or before Fy pa naman, no? That is from here up to here. Okay, until Fy. So, okay lang. Ano yun? Ganda yun. Okay, that it will locally buckle immediately after reaching Fy. Now, if the slenderness ratio B all over T is less than lambda P, then the element is compact and it will locally buckle much after reaching Fy. So, yeah, okay din yun. If it is less than lambda P. But if we lambda is AISC, pero sabi ng NSCP, ayun natin okay lang pala. If we to thickness ratio of one or more compression elements exceeds lambda P, but does not exceed lambda R, the section is non-compact. Now, if the weight to thickness ratio of the element exceeds lambda R, the section is referred to as its slender elements. Okay. If the weight to thickness ratio of one or more compression elements exceeds lambda P, but does not exceed lambda R, the section is non-compact. If it exceeds lambda R, the section is slender. And and it must not exceed the limiting weight thickness ratio. Lambda P. Okay. So ito na. Next statement. If all the plate elements of a cross section are compact, then the section is compact. But if any one plate element is slender, then the cross section is slender. Paano ba natin yun maano? Okay, instead of using this statement, let me highlight this. All right. So here, if B all over T okay is or ito din yung specification. It is compact. Compact if its flanges must be continuously connected to the web all throughout the full length of the member. Then we can say that it is compact. Madali lang naman yan ma-state. Or if B all over T or H all over T ratios, okay, it should not exceed, it should be less than or equal to lambda P, then we can say that it is compact. Okay? If the width to thickness ratio of one or more compression members, that would be B all over T, exceeds lambda P, is greater than lambda P, but does not exceed lambda R, but is greater than or equal to lambda R, then it is non-compact. And if it exceeds lambda R, with thickness, that's not wedge, and the width thickness, T over T exceeds lambda R. Tama ba? And it should not exceed 10 ito. Maliit. It should also be less than. Right. So if it exceeds, it should be less than lambda R, then that element is now slender. Ito yung slender element section. Okay, yung tatlong yan. Okay, I will save this at isa-send ko lang. Alright. Naguguluhan ako sa module. Right. Now the slenderness limit lambda P and lambda R for various elements with different boundary conditions are given in the tables. Okay, yung dalawa lang. Denote that the slenderness limit lambda P and lambda R and the definition for plate slenderness and the over the ratio depends upon the boundary conditions for the plate. Ano yung boundary condition? If the plate is supported supported along two edges parallel to the direction of compression force, then it is a stiffened element. Anyway, dito naman sa table, makikita natin if it is stiffened or unstiffened element. Ito yung lang. Alright? Sabi niya, it is supported. It is supported on two edges parallel to the direction of compression force or compression force. Okay, kaya, let's go to the stiffened elements, no? Yung table 2. Okay, hindi ko na nilagay sa module. You have to look for it sa NSCP. Binigyan ko naman kayo ng NSCP, no? You just have to download that in sa CS natin. Ito yung stiffened elements. Saan ba yung compression natin dito? Number 10, uniform compression in webs of doubly symmetric I-shaped section. Yung webs kasi kino-consider natin dito. Plus. Okay? So, parallel to the compression force, ito yung web natin. Ito. Pangit. Ito yung web natin. Itong part na ito. And it is supported. Okay? Or merong stiffening material dito sa magkabilaan niya. Ano yun, sir? Yung flanges. Okay? Itong flange na ito. Okay? Stiffened our web member. Okay? So, element stiffening lang ito. So that, stiffen yung ating web. In that case. Alright? Kaya nandito siya sa stiffened elements. So, it's true for saan pa ba yung iba? Uniform compression in stems of T. O, ganun din dito. Our T is also a stiffened element. Saang banda, sir? Dito sa part na ito, no? Kaliwat kanan niya. Okay, and then ano pa? Number 12, of course, I is stiffened on both sides. Okay, since that is an HSS. Okay? Or hollow structural section or rectangular box. Basta ganun, no? It is stiffened element. Paano naman yung unstiffened, sir? Okay, nandito naman. And we always consider number 3, number 4, and number 5 for compression. Okay, the plate is supported, if the plate is supported along one only, or along one edge only, parallel to the direction of the compression force, then it is an unstiffened element. So, unstiffened daw, yung mga flanges ng W shape, okay, itong channel. Why? Because itong web ng ating, flange ng ating channel, itong ano na to, it is only supported along this part. No? So, one way lang or on one edge lang yung support niya. So, that is an unstiffened element. Itong channel. Okay, itong may stiffening lip na ito. Ito. So, that this part here, plus, ay merong stiffening on this side. Okay, may stiffening on this side and on this side. So, this is a stiffened element. I hope that's clear. Okay. So, the local backplate state can be prevented from controlling the column strength by using sections that are non-compact. So, if all the elements of the cross-section have calculated slenderness ratio B all over T less than lambda R, then the local buckling limit state will not control. Ito na yun. Okay? Kung yung B all over T daw class ay mas mababa kay lambda R, then the local buckling limit state will not control. Okay? So yun dapat ang titingnan natin. Si B all over T should be less than lambda R. Or if all the elements of the section are calculated slenderness ratio less than lambda R, then the local buckling limit state will not control. So mag-go-over na yung ating yung mga formulas natin sa taas. So ano ba yung consider natin kanina? That B all over T is less than lambda R. Nasa gallery na. Wait lang. Eto. Less than lambda R. Ito dapat. It should exceed lambda P, but does not exceed lambda R. Bali pa rin yung ano dito class. It should not exceed lambda R. Exceed to the N. It should be less than kung hindi niya dapat may exceed. Right? Ganyan dapat siya. So, yung other. Okay, considerations. Okay, kung gusto nyo mag-refer lang sa inyo. Pero ang labo, ewan ko, screenshot ko lang yata yan sa libro. Kaya ang labo. If you want it clear, then you can check the NSCP. So example number 2, before we end this lecture. So we have a double 14 by 74. Yung section ng example natin kanina. Okay, and determine the local buckling slenderness limit and evaluate, okay, using the length of 6 meter and pinned ends. Okay, also A36 is used. Okay, A36 na, hindi na A992. Okay, does local buckling limit control or limit the column strength? I-evaluate lang natin class if, okay, local buckling will limit the column strength. Okay, if it does, then it is not covered here. Okay, it might be covered in your higher structural design subjects. Okay, we will only cover here when the flexural buckling limits the column strength. So step 1 is we calculate the slenderness limits. So from your AISC section database, okay, hanap niyo naman na, okay, yun yung example natin kanina eh. So Fy, of course, for A36, Fy is 248 megapascal. That is a weight constant. So lambda R, wait lang, is, check muna natin. Our section is W. So for flanges, we will consider for flanges and class webs. Okay, we go to NSCP. So compression in flanges of rolled I-shaped sections, that's number 3. Ano ba yung consider natin? The B all over T ratio, the width to thickness ratio class is B all over T. Okay, and we compare it to 0.56 square root of E all over Fy. That's for the flange. What about the web? Since the web is stiffened, we have this consideration. Okay. Lecture number 9. Tama ba? Lecture in webs of doubly symmetric I-shaped sections and channels. Since it is doubly symmetric, ibig sabihin, it is symmetric along the x and y direction. Okay. Our width to thickness ratio is h all over t sub w. Yung h, in-explain ko na kanina kung paano hanapin. Okay. And for lambda p, we have 3.76 square root of e all over fy. And for lambda r, we have 5.7 square root of e all over fy. Alright. So we check here. So lambda r for the flanges is 0.56 square root of e all over fy. So direct substitution, then we have 15.9. What about the webs? Okay. For lambda r, it is 1.49. Tama ba? I-check natin. Mali. Lecture in webs naman kasi ito. Ito, class. H all over T sub W versus 1.49 square root of E all over Fy. Okay, uniform compression. Lecture pala yung tinitignan ko kanina. Number 10. Okay, 1.49 square root of E all over Fy. So direct substitution, since our Fy is 48, we have 40.41. So, we compute the slenderness or thickness ratios for flanges and webs. Okay? Ano yung B all over B okay, for flanges, that's BF all over twice the thickness of flange. Mahanap naman natin yan, class, dito sa section database. Saan ba yun? Our section is W by ano na yun? 14 by 74. Ito. Saan yung BF all over twice thickness of the flange? Makikita nyo din dito, class. Sana yun. Joke lang pala. Alam ko meron yun eh. Okay, ito. Yan. Meron tayong 6.41 for the B sub F all over twice the thickness of the flange. Check nga natin. It's 6.41. What about the webs? It is H all over T sub W. Okay, so hindi ka naman problema for the determination of the H. Meron na rin naman dito. Given na siya. It is 25.4. Okay? So 25.4. So i-compare mo lang. Make the comparisons and comment. Okay, for the flanges. Flanges, ha? Saan yung flanges natin? That's B all over T. Or B sub F all over twice the thickness of the flange. Okay, it's 6.41. And i-compare mo siya for 15.9. Okay, it is less than lambda r. So therefore, the flange is non-slender. Diba? So, sabi natin, sana yung ano. We go back here. Okay. If the width to thickness ratio of any element exceeds lambda r, ito ha, if the width to thickness ratio of any element exceeds lambda r, sabi niya dito, the section is referred to as a slender element. Pag na-exceed niya yung lambda r class, our section or local backlink will not govern our tama ba? If the width to thickness ratio of the element, the section is referred to as slender element. Kapag it should be non-slender para hindi mag-govern yung ano. Kapag na-exceed niya itong lambda r, okay, yun na yung hindi na pwede yung mga formulas natin sa taas. Okay, so it should be less than lambda r. And then for the webs, since it is also less than that, then our web is non-slender. So in such case where the flanges in the webs is less than lambda r, or the ratios or width to thickness ratios is less than lambda r, our section is non-slender, in which case hindi mag-govern ang local buckling. So local buckling will not limit the column strength. So it is permissible to use a cross-sectional shape that does not satisfy the width to thickness requirements. Such member may not be permitted to carry as large a load as one that does not satisfy or does satisfy the requirements. In other words, the strength could be reduced because of local buckling. The overall procedure for making this investigation is as follows. With the width to thickness ratio lambda is greater than lambda r, okay, we use the provisions for section 505.7 in our NSCP and compute for a reduction factor Q. Okay? So yun, pwede daw yun. But we introduce a reduction factor Q. And we can read in section 505.7 on how we determine that. Alright. So we have here another example for column design. Parang kulang itong i-check ko to. Parang kulang ito. Okay. So, anong column design example? Determine. Hindi naman ito column design eh. The design strength for ASTM A992 W14 by 132 is part of a braced frame. Assume that the physical length is 9 meters, the ends are pinned, and the column is braced at the ends only for the x-axis and braced at the ends and mid-height for the y-axis. Okay, so ito yun, may bracing class doon sa y-axis na. So that the LY class, diba, since may bracing doon sa mid-height, may mahahati na instead of the length of 9 meters, it will be 9 divided by 2 or 4,500 mm na. Whilst for L sub x, the length along the x or the major axis, it is braced at the ends only. Ibig sabihin, it will be 9,000 yung buong length. Ganyan siya. Okay, ASTM A992 is again Fy being equal to 345 megapascal. And our section is W14 by 132. The section details, hanapin mo sa section database. So here, the solution step 1 is to calculate the effective lengths. Okay, so ito yung mga details ng W14 by 132. R sub x is 160, R sub y is 95.5, and the gross area is 25,000 square millimeter. Okay, since it is pinned at ends, sabi niya dito, our kx and ky is 1.0. Okay, so L sub x is 9, L sub y is 4.3 meters. It's 9,000 mm and 4,500 millimeters. So kx lx, you just multiply that, is 9,000 and ky ly is 4,500. Now, determine the governing slenderness ratio. Our kx ls, our effective length, and ky ly, okay, you just divide it by the corresponding radius of gyration, which is r sub x or r sub y. Okay, depending on the major and minor axis. This is the major, and this is the minor axis. So, direct substitution, 9,000 over 160, we have 56.25. 4,500 divided by 95.5, we have 47.12. Now, di ba nakita nyo dito? In our last example, ky ly all over r sub y ang mag-govern because it has larger values. But because of the bracing in the mid-height, okay, along the minor axis or the weak axis, okay, ang mag-govern na ngayon na slenderness ratio ay yung mas malaki, which is now in our major axis is 56.25. So larger slenderness ratio, therefore buckling about the major axis will govern the column strength. Okay. So magbabuckle siya possibly along the major axis or along the x-axis, not in the y-axis. The column strength, F sub E. So, direct substitution lang yan since our governing is 56.25 na. Then, pi squared E over KL over R squared. We have 623.86. Ito yung sabi ko, no? Mamaya. And then, we check the limits. Okay. Ano yung limits? We have 4.71 square root of EL over Fy. That is 113.4. Ano yung pinakampat na yan? Our slenderness ratio, 56.25. Yung 56.25 over EL over R is less than 4.71 square root of Fy. Our FR is still 1.65 raised to Fy over Fe of Fy. Alright? So therefore, ito, substitute lang natin yung mga values. We now have 273.71 megapascal. Again, no, this is our critical buckling stress. And ma-determine mo na it is always less than 1. Okay? Or less than or equal to 1 of our Fy. Okay? Itong ratio kasi na ito is less than 1 eh. Okay? So it is 273.71. So the nominal strength now is our FCR, we multiplied that by our gross area. So 25,000 by 273.71, you just divide that by 1,000 para ma-express mo siya in kilonewton. What is the capacity? Okay, it is 6,842.75. That's the nominal strength. So considering LRFD, design column strength, we multiply that by 0.9, then we have 6,158.48 kilonewton. That's the capacity for LRFD. Now, we check for local buckling limits. Okay, yun ba talaga yung mag-govern? We have to check. Our BF over twice thickness of the flange is 7.15. Remember, our section is W14 by 132. Okay, lagi naman natin yan makahanap class sa 14 by 132. Section database, yung mga BF over twice the thickness of the flange, that's 7.15 and 17.7. So, hindi ka mahihirapan maghanap niyan. Okay? 7.15 and 17.7. Okay? And then you compare it with lambda R. Okay, that's 15.9 and 42.31. So, since both width to thickness ratio is less than lambda R, we therefore conclude that the section is non-slender, so that local buckling will not govern the column strength. So, okay na siya. Alright. Now, you go and study example 4.4. Okay? And then, if for questions, you can always message me or message our group chat para matulungan ko kayo. No? And this is the design part class. Since meron naman ganyan class, sabi niya na 10 a.m. Okay? So, pasadahan lang natin. Mag-message lang kayo kung nagtatawag na si Ma'am Abby at kailangan na natin umalis.